Well, is this the definite integral calculator? Yeah, I'm not sure. I think if we don't put these in, then we might, I think it might just give us. So this is the integral calculator here, and you can check with this. And this, what I like about this one is it actually shows you, it should show you the steps. So let's just see what happens here. I don't know if it's going to cry at the fact that we don't have an integral. No. Okay. So manual integration. So what they might do here, and again, we can see if this resonates with our answer. Oh, here's the steps. So what they suggest is, yeah, splitting these up into partial fractions, or splitting this up into partial fractions. And does that line up with what we have here? So we have, let's see, what is that, negative 1/8. Yeah, so they just do that in a bit different order. We have all the same thing. Okay. So yeah, so with these steps here, they take the constant out, and you know, of course, we have the natural logarithm for the ones that have a -1 kind of exponent, and then for the others, you use sort of this this power rule of integrating. And so they show you all the steps here, which I really like. It's nice to kind of see the steps. Sometimes they use, you know, little different methods that maybe we, as really the high school, you know, level integration, maybe there's other things, other little shortcuts and stuff that may not be, you know, easily applicable here. But anyways, you should get the final answer, and you can always double check your manual work with this. So yeah, I don't know, I haven't checked this myself here yet, but let's see if it looks fairly reasonable. So does this compare with what we have written here? Let's see if we can take a look at it here. So we have the -1/8 of this ln of x minus 1. That looks good. And we have a positive 1/8. So they have that all in one term. That's great. The -9/4 and x to the x minus 1 to the -1 is there. And then, of course, the 1/4. And there we go. Plus c at the end. And we're good. So that integral calculator is kind of a nice little thing to have in your back pocket there in case you want to double check anything you do. Okay, so let's, now gone through that, let's start from scratch. Let's do this one from scratch, remembering what we did yesterday, partial fractions, and then integration. So I'll give you a chance to write that down. Okay, so of course, when we look at this, if we could do use substitution, right, or if we think we could do integration by parts, if you want to, you know, evaluate that and see if we can do that, you're going to notice that use substitution here. Well, we have another x term, right? The derivative of x plus 3, which would be the inner function, is 1. We have to manufacture an x. That's not a good thing. So what we're going to do is we're going to basically look at this as a rational function, and we're going to try and split it into the sum of its partial fractions. So with this repeated binomial factor in the denominator, we're going to look for an a number here, a constant here, over x plus 3. And then we're also going to look for a b over x plus 3 squared. So we kind of need to build it up. And then once we find that, of course, we can now take the integral of each of these pieces, which is going to be pretty easy. And then tack on a plus c, and then we're going to be good to go. So let's see what we can do here. So x plus 5 over x plus 3 squared equals a over x plus 3 plus b over x plus 3 squared. Okay? So we're going to eliminate the x plus 3 squared, right? And we're going to end up with this right here. Okay? So we're going to end up with x plus 5, right, equals a. Now, if we can expand this out, I think that would be reasonable. Ax plus 3a plus b. Okay? And then this, of course, this is going to. All right, so two different things we could do, right? We could equate the coefficients on each side. We could just do substitution. I already expanded this, so the substitution you might want to do before you expand, but I'm thinking of the coefficient equations here. So obviously we have the x term and the x term here. So from that I know that a must equal what? 1. Yeah. And then if you look over here, the constant term is 5, and here the constant term is 3a plus b. So this one's a pretty easy one, isn't it? 3a plus b equals 5. I know that a is 1. So now I know that b is 2. Okay, you good with that? A is 1, b is 2. So we can take it from there, and I'm just going to erase some of this part so I can keep this all on one screen for us. And now what we can do is fill in our values. So I'm going to take the integral of 1 over x plus 3 dx plus the integral of 2 over x plus 3 squared. Let's see. So now we actually integrate here, and this is going to be the natural logarithm of x plus 3, right? And this one's going to be 2 times, we'll pull that 2 out, right, as a constant, really. That would be a nice thing to do. We don't have to, but we certainly could do that. So 2 times this integral here. So this is actually going to be, and if you want to rewrite this, you can, but you certainly wouldn't have to. That's going to be an x plus 3 to the negative 2. All right? So we're going to add 1, and we're going to go 1 over, and negative 1 is going to be our new exponent there. So it's going to look something like that, plus c. So this should be, oh, whoops, that's going to be a minus 2 times a negative 1. So we're going to do a negative 2. And then if you want to write this, I'll give you this option here too. Probably be a good idea. Plus c. And is that what you guys got? I think you guys were blistering away while I was taking my time to explain, so great. I did my math right. We got the same answer? Okay. So, like I said, yesterday we did the heavy lifting with working through the partial fractions, so now it's just integrating, which is sort of the easy part. So, and again, if you want to pop this into your integral calculator, just to double check, that would be great. So I think now, oh yeah, I have the answer here that I was going to scroll down to as well. So yeah, it looks good. Now notice that I started doing this, and the reason why, you know why I'm using k? Because in our partial fractions work, a lot of times we have a constant c. Okay, so in that case we didn't have a c because we only had we were only looking for a and b. But this could be still constant. But anyways, if you end up using a c here, don't use another c in your answer. Use a k or something. So we're going to try and maybe start doing that a little bit more. K for constant or whatever you want to use. Okay. All right, so, yeah. Let's see, I think this is the assignment I want to give you, so just give me 1 second. I'll